start by sharing the presentations. So I'll start the first one.
Hello, everyone. I'm Wenpeng He from Huazhong University of Science and Technology. Today, I'm going to present H2 ORAM, low response latency optimized ORAM for hybrid memory systems. Non-volatile memory, such as Optane DCPM, are potential DRAM alternatives as it provides large capacity, low latency, better addressable non-volatile data storage. But it also faces two problems. The first one is a limited write endurance problem. Attackers can destroy NVMe DEXs by repeatedly writing a memory cell to exceed its write endurance limit. The second one is information leakage. As the data is persisted in the NVMe, the content can be easily obtained by scanning the memory. Not only that, recent studies reveal that memory access patterns can also leak confidential information. Fortunately, ORAM can prevent these attacks through memory encryption and address obfuscation. RealRAM is a state-of-the-art ORAM scheme for a secure processor. It organizes memory as a binary tree. Each node in the tree is called a bucket. Each bucket contains one metadata block and Z real nodes for real blocks, S dummy nodes for dummy blocks. To fetch a block from memory, the path where the block is located is checked in the port map. And then, all metadata blocks on the path are read to find out which bucket contains the target. Last, one block is read from each bucket on the path. To avoid such overflow, after multiple rounds of read paths, a write path is executed. The write path first reads all valid real blocks on the path and then evicts the sharper blocks from such to a path. Although using ORAM to protect the NVMe security is attractive, it also faces two challenges. The first one is the write amplification of ORAM that worsens lifetime of NVMe. The second one is the slow NVMe reduces system performance. Aiming at the first challenge, we introduce hybrid memory systems. In the ORAM tree, the number of writes increases exponentially from the leaf bucket to the root bucket. This causes the up NVMe load to wear out quickly. So, we catch the top line levels on chip, map the bucket in middle levels to DRAM, and the rest to NVMe. This can reduce 73% write traffic to NVMe, with small cache and DRAM storage overhead. The NVMe is 2 times to 4 times slower than DRAM. As the figure shows, the higher response latency reduces system performance. For this reason, we propose 3 schemes to keep more hot data accessible from DRAM. The first one is LFUP aging, a frequency-based evocation scheme. It sorts the data blocks in the stash according to their access frequency, and the call date is first evicted. As the figure shows, in the write path, buckets are filled in the order from the bucket 3 to the bucket 1. As the block C is hotter than block A and B, it will be stored in DRAM. The second scheme is mask slots. It's a new type of slot in DRAM bucket that is used to store the duplicates of hot blocks. When the hot blocks A and B are stored in NVMe, their duplicate, block alpha and block beta, are created in the stash. Then these duplicate blocks will be stored in the mask slots. Last, we find that the fixed slot partition leads to the waste of effective DRAM space. So we dynamically adjust the bucket composition to store more hot data in DRAM. The empty real nodes can be used to store the duplicates, and the empty mask nodes can also be used to store the real blocks. We compiled the proposed 3 schemes with the baseline Ringo RAM, and the results show that our work improved the DRAM hit rate from 36% to 72%, reduced 44% response latency, and achieved 18% performance improvement. Thanks for your listening.
All right. Thank you.
Okay, good afternoon, ladies and gentlemen. Once again, thank you very much.
Let me.
Hello.
Let me go back to this screen. Thank you to Wenpeng for the recorded presentation. And does anyone have any questions for Wenpeng? So if there are no questions, I guess I'll ask a question. So one issue with the hybrid memory systems is that the latency is different between the 2 levels in the memory. And so does that kind of leak any information that you wouldn't want to be leaked?
Yes, can you hear me?
Yeah, I can hear you.
No, our work doesn't need hot data access patterns. In ORAM suite model, the memory is insecure and untrusted, but the processor is secure. Our optimizations will change the memory access patterns of Ringo RAM. This means whether the data block is a hot block is not known from the insecure memory accesses, and the processor is the only one that knows when the data blocks is fetched to cache. It's not possible for attackers to obtain the data response latency from secure processor. Therefore, the access pattern of hot data will not be known by the attackers.
Okay. Yeah, great. Thank you. So, so I'll move on to Rui Zhu, who is our next speaker, and I'll play the video, and then if anybody has questions, we can ask after that.
Hi, I'm Rui Xu. The title of my report is Optimizing Data Placement for Hybrid SPM with SRAM and Racetrack Memory. I will report from the following aspects. In IoT era, embedded devices require small size, low energy, and low latency. Scratchpad memory is managed by software that has a higher density, and non-volatile memory is used in embedded system, and it has higher density than SRAM. For energy and latency, they depend not only on computation performance, but also on memory access performance. In this paper, we focus on access performance. Nowadays, data is exploding. If the memory is small, there will be much memory miss. It reduces the performance of system. Thus, increasing the memory capacity is important. NVM is potential because NVM has the advantages of high density, but addressable, such as PCM, STT-MRAM, 3DS point, and restrict memory. But the most of NVMs have limited endurance and high write cost. Fortunately, RM has high endurance, high density, and high access performance. Thus, RM is more potential. This is a schematic of RM, as shown in this figure. The access port is a magnetic tonal junction of sandwich structure. During data is accessed, if the data to be accessed is not aligned with the access port, data on the tape must shift, so that the accessed data is aligned with the access port. Now, we use an example to illustrate the process of RM data access. The access sequence is A, B, C, A, D. The first data is B, accessed is A. Due to A is aligned with the access port, there is no shifts. The second data to be accessed is B, but B is not aligned with access port. The data in RM is to shift one position to the left as a whole. This is a one shift operation. 2 shifts. 3 shifts. 2 shifts. The total number of shifts is 8. Although the cost of one shift is very low, the cost of multiple shifts are very high. Meanwhile, although the access performance of RM is close to that of SRAM, the write overhead is still greater than that of SRAM. Thus, using RM as SPM, there are 2 challenges to address. They are shift operations and longer write latency. There are many works to optimize the data placement for RM, but there are still many data that require many shifts when they are accessed. We call this as jump, especially when the jump exists in the loop. The shifts will increase sharply. Thus, RM is more suitable for sequential access to data. Therefore, we use SRAM to store data that needs to be jumped to access. We proved that after placing the data on ARM to the SRAM, the total number of shifts must be less than or equal to the odd number of shifts. Now, we use an example to illustrate the above theorem. Assume that data B is placed on ARM and the position of other data remains unchanged. The first data to be accessed is A. There is no shift. The second data to be accessed is B. There are still no shifts. Because B is placed on SRAM, shifts is not needed. 3 shifts. 3 shifts. 2 shifts. The total shift number is still 8. But if the subsequent data of B is moved forward, the gap will be filled. We can see the shift of data changes like this. The total shift number is 5. However, the density of SRAM is very low and the stacking power is high. The less of SRAM using, the better. Thus, the objective of our study is maximum performance improvement while minimizing the size of SRAM. This figure is the architecture of the hybrid SPM with SRAM and RM. They are uniformly addressed. The CPU can load store data from to them directly. For the proposed hybrid SPM with SRAM and RM, to take the advantages of SRAM and RM better, the technical challenges as follows. Which data needs to be placed in SRAM? How much data needs to be placed in SRAM? Thus, we propose largest write and shift reduction schema. It decides what data to place on SRAM. To further increase the capacity of SPM, it reduces the using of SRAM. LWSR1 decides what data to place on SRAM. It will pre-place the data on the RM according to the strength of first access, first placement. Due to the shift operation of RM and the write operation that is more expensive than SRAM writes, the PLC2 shift is proposed to present the cost of data on RM. Next, the process of LWSR1 is given. LWSR1 computes PLC2 shift firstly. Then, select the data with the largest PLC2 shift and the least number of reads from this data. Put the selected data on SRAM. Next, reorganize the data placement on RM. If the SRAM is not full, continue to compute the PLC2 shift based on the new state when SRAM is full. And data movement. To improve the capacity of SPM, LWSR2 is designed to reduce the size of SRAM. Reducing the size of SRAM will bring performance loss. Thus, We define the shift loss and the cost loss. Therefore, LWSR2 uses a descent parameter to move the data, which have the lower pseudo shift on SRAM to RM, to reduce the size of SRAM until the shift loss and cost loss are not be satisfied. We use an in-house simulator to evaluation. There is one kbit SRAM, 4 RM part, one tape with one access port, and we use night tracings from mid-bench, where there are 3 large workloads. In order to select a suitable descent parameter to reduce the size of SRAM, we conducted experiments on these anti-parameters. We focus on 2 factors, the size of SRAM and convergence time, but we pay more attention to the size of SRAM. Therefore, when we assign different weights to these factors, we select the first 3 parameters under different weights. We found that the parameters selected under different weights are not much different. The following parameters are using 0.3 as the descent parameter. We use SPM with pure SRAM, FCFS, and SOA for SPM with pure RM as the baseline. For hybrid schemas, WA, LMR, and LWSR are compared. We can see the number of shifts under pure SRAM is 0. This is because the SRAM does not require shifts. The latency under pure SRAM is smallest. This is because SRAM does not require shifts and its access latency is also very low. FCFS is the worst. This is because it does not consider any data access patterns. WA and LMR are better than FCFS and SOA, but they are worse than LWSR. This is because FCFS and SOA are only using RM. Although WA considers rest, it does not consider shifts. LMR considers shifts, but it does not consider writes. And if the data on RM is moved to SRAM, the shifts will change, but LMR does not consider it. Moreover, LWSR considers all of the factors mentioned above. For error, the error of SPM under pure SRAM is the largest. This is because the density of SRAM is very low, and the error of WA, LMR, and LWSR is the same. This is because WA and LMR use the SRAM size obtained by LWSR. The large workloads have the same trends with small workloads. Now, summarize the work. We observed the performance bottleneck for RM is shift operations. RM is more suitable for sequential access. We proposed 1 metric and 2 schemas. We evaluated. Our proposed schemas are effective. That's all. Thank you.
All right. So thanks to Rui for her presentation. And does anyone have any questions? Otherwise, I'll ask a question. So, so what exactly is the overhead of data migration between the SRAM and RM? And is that like it's not clear why a smaller size of SRAM at any point will be good for performance if the overhead is moving data back and forth between SRAM and RM is too high. So can you comment on that?
Hi, can you hear me?
Yeah.
Oh, okay. The proposed techniques are based on compiler, and no physical data migration will occur. They are primarily targeting offline, and it means the data placement generated by our method is initial placement. Thus, there is no data migration overhead between SRAM and RM, and we will perform online data migration later to improve performance further. Thank you.
So the overhead is not too high, is that what you're saying?
Pardon?
So the overhead is not high? The migration overhead?
Yes, there are no real physical data migration, and it is based on compiler.
Okay, all right. So, okay, thanks for your answer. Does anyone else have any questions? Okay, so thanks to Rui again, and we'll move on to Chao Xuan, who is I'll first move to his recorded presentation, and then we'll see if somebody has questions at the end.
Hi everyone. Today's cost-centric mindset for DRAM fabrication makes the DRAM latency not scale as much as its cell density. Before going to the details, let's talk about some DRAM basics. This is a structure of DRAM chip. Each chip has multiple banks, and each banks have multiple subarrays, and all subarrays share global sense amplifier. The subarray consists of multiple tiles. Each tile has 512 word lines and 512 bit lines. The bit lines are connected to the local sense amplifier. The intersection of the local word lines and bit lines is a DRAM cell, which has a transistor and a cell capacitor that store logic bits 0 and 1. DRAM operation has multiple commands. Basic reading and writing involve charging and discharging of the local and global bit line. And the capacitance of both bit line depends on their length. This capacitance value is the major contributor to different timing parameters as shown in this table. This timing parameter dictates the DRAM access latency. Therefore, reducing DRAM latency requires reducing the local and global bit line lengths. So one way to reduce the latency is to reduce the length of local bit line. The figure here shows a DRAM bank that contains 512 cells per bit line in each subarray. Zoom in the tile, you can see the bit lines connect to the local sense amplifier, the precharge unit, write driver, and the sense amplifier I/O. The total length of this circuit block is about 1/4 of the bit line. This figure is showing 256 cells per bit line structure with the same bank capacity. The required number of subarray had doubled, therefore the length of the global bit line, which goes across the bank, has increased. From our latency area trade-off analysis, we can see that the overall access latency increases while we are shortening the local bit line. Therefore, there's a need to simultaneously reduce both local and global bit line length in a way that does not substantially increase the DRAM bank area. So maledictive 3D technology enables processing and integration of multiple tiers of logic circuits on the same die. Compared to the traditional 3D structure that uses through-silicon vias to connect different dies together, monolithic inter-tier vias of M3D technology has 10,000 times smaller than a dimension than the TSV, so that we can achieve very fine-grained vertical interconnects on the single die. For designing DRAM with M3D technology, our idea is to put the sense amplifier on one tier and the DRAM cell array on the other to improve the latency area trade-off. But the challenge are due to the limitations of M3D fabrication process. We need tungstens to realize the interconnects at the bottom tier, which has worse resistivity than the traditional copper interconnect. At the top tier, the transistor performance degrades due to the required low temperature M3D fabrication process. To overcome these challenges, our proposed idea for designing M3D DRAM is to place the DRAM cell array on the top tier to avoid the interconnect performance penalty. We put the sense amplifier and the other peripherals on the bottom tier to avoid transistor degradation. As you can see in figure C, in our proposed M3D DRAM design, we can reduce the local bit line length to 128 cells per bit line and still achieve the global bit line length shorter than the conventional 2D DDR4 design. Let's look at the cross-section of the vertical interconnect. The local word line driver connects to the local word line through metal 1 to metal 5 and MIVs. The same method applies to the sensor provider connects to the local bit line, and sensor provider I/O connects to a local data line. Our analysis shows the extra resistance and capacitance from the vertical interconnects actually does not increase the latency or energy consumption significantly. We analyzed the timing constraints and an area with LT spice and cacti. Our analysis shows that the M3D can relax the latency area trade-off by moving the trade-off curve closer to the origin. We select DDR4 with 512 cells per bit line and M3D DRAM with 512 and 128 cells per bit line for our system level analysis. We do a Gen 5 and NV main based full system simulation with parsec benchmark application, and the result shows 9.5 less latency and up to 21% less energy delay products with 14% less DRAM die area compared to a conventional DDR4. In conclusion, we show how the fundamental latency area trade-off for DRAM can be mitigated by using M3D technology. We evaluate the latency area trade-off for various configurations. Our design is quite beneficial. Thank you.
All right. Thanks for the presentation. And does anyone have any questions? So, Xiaohang, if you're online, so one question I had is, so you ran your experiments, your performance experiments on Parsec. Did you try any other set of benchmarks to see how this proposal will be beneficial?
Actually, no. I only tried that on Parsec benchmark for now. Can you hear me?
Yeah. Okay. Yeah. So, do you expect this like this technology to behave any better or worse if you use like more realistic applications, not like small kernels?
I would say it will, because it's reducing the access latency, the fundamental access latency. Although it did not improve any bandwidth or so, but the overall timing constraints will reduce. So I could say that it could use in other benchmark applications or general purpose like that.
Okay. All right. So thanks again for your presentation.
Thank you.
And I'll move on to the last presentation of this session from Bumjun Kim. And I'll play the video first, and then we'll see if anybody has any questions.
Hi, I'm Bumjun Kim. I'll present ADAM, Adaptive Block Placement with Metadata Embedding for Hybrid Caches. Today, on-chip caches occupy a large portion of the on-chip area in the modern processors. However, ever-growing working sets of modern applications require larger on-chip last-level caches. SRAM, the conventional memory for last-level cache, does not scale well because of its high power consumption and low density. STT-RAM can be an alternative to SRAM. It has higher density than SRAM and lower leakage power consumption over SRAM. But STT-RAM also has problems, because it has long write latency and high power consumption on write operation. Both types of cache has pros and cons, so the hybrid cache have been proposed. Hybrid cache has two data array regions. Write-intensive blocks are allocated in SRAM region to mitigate long write latency of STT-RAM, and as the read latency of STT-RAM is low, read-intensive blocks are allocated in STT-RAM region. Thus, optimal block placement policy is crucial for hybrid cache. In prior works, block placement policy predicts write intensity of blocks when they installed, and after they have installed, they learn the actual write intensity during execution. However, when a block is evicted from the cache, the write counter value of block is also removed from the cache. It means when a block reinstalled, it has to relearn their write intensity. This can limit the improvement of performance. The write intensity of a cache block is constant during the execution across several workloads. On average, the write intensity is not changed for 98% of the blocks. This means the write intensity of the block can be used to predict the future write intensity of the block once it is learned. Our key idea is embedding the metadata within the cache block. We will compress 64-byte block to 61 byte. When it compressed, the metadata will be embedded in the rest space. Also, 2 byte of signature indicates whether the block is compressed or not. Components of Atom framework. First is per block write counter. It's located in tag array with text. It's 3-bit saturated counter. It increases 1 on a write hit and decreases 1 on a read hit. Second, the write intensity detection unit. When the block is evicted from cache, it compares write count value of victim and write intensity threshold. After comparison, it generates 1-bit metadata representing the write intensity. Next is metadata embedding unit. Compressor compress the block, and after the block compressed, place metadata within the cache block. Last is the block placement unit. The compressor decompresses the block and extracts metadata. With the extracted metadata, block placement unit determines which cache to place the block. Then just place the block in right place. The operation of Atom. First is write operation. When the victim is selected, it's evicted from cache and ready to be compressed. If the block is compressible, the block will be compressed and the metadata will be embedded within the block. Finally, if the block is dirty, it will be written back to main memory. Next is read operation. After a read or requested block from main memory, check the existence of metadata. Then, extract metadata from block and decompress the block. Finally, after checking the metadata, allocate the block to write data reason. Atom also has special operation to clean write. In conventional cache system, dirty victim is written back to the main memory, but clean victim does not. But in Atom, clean victim can be written back to main memory only if when the write intensity is updated. The reason is because of this part of write operation. Atom have to track the write intensity perfectly for a precise prediction, so we decided to write back the clean victim whose write intensity has updated. Fortunately, clean write victims only have small portion of all victims, so they will not affect much to the performance. The table is our baseline system configuration. We used trace-based hybrid cache simulator based on USIM, and we utilized memory-intensive benchmarks from SPEC 2006. Performance impact of Atom. On average, Atom improves performance by 24% from baseline. For the clean write method, it improves performance furthermore. On average, Atom with clean write achieves a speedup of 26%. Hybrid cache needs effective block placement policy. Precise prediction of write intensity is needed to reduce the overhead occurred by misprediction of write intensity. So we proposed Atom, and Atom is a new adaptive block placement framework with metadata embedding for hybrid caches. Atom enables the storage of metadata without additional storage elements. Please read our paper for specific results, and thank you for listening.
All right, so thanks for this presentation. And any, yeah, this YouTube plays automatically in the next video. So, sorry. So, does anyone have any questions? So I guess one question I had is one of the issues with STTRM is that its write endurance is obviously not great. So does this mechanism with compression increase the number of writes to STTRM, or is it mostly the same as the original system without compression?
Can you hear me?
Yeah.
It increases write operation on STT-RAM.
So what percent increase do you see? Like, does it increase by like 10% or 2x, or what is the average number of writes that you add on top of the baseline?
If we predict write intensity precisely, migration will not be much occurred. Yeah.
Okay, so if you predict it precisely, then There won't be that much overhead. If you don't predict it precisely, then you'll have a bunch of extra writes.
Yes.
Okay, all right. Any other questions? Okay, I think we are out of time. So thanks to all the speakers for their prepared presentations and for answering the questions. And thanks to all the attendees. And I think this is the end of, this is the end of the today's presentation. So hopefully we'll see you all tomorrow morning.
Awesome. Thank you, Doctor. Thank you so much.
Thank you.